Good day. I'm Bayla, and I'm going to discuss about solar radiation analysis. Incoming solar radiation or insolation received from the sun is the primary energy source that drives many of the Earth's physical and biological processes. Understanding its importance to landscape skills is key to understanding a broad range of natural processes and human activities. With landscape scales, topography is a major factor that determines the spatial variability of insolation, variation in elevation, orientation, and shadows cast by the topographic features all affects the amount of insolation received at different locations. This variability also changes with time of day and time of year, and in turn contributes to the variability of microclimate, including factors such as air and soil, temperature regimes, evapotranspiration, snowmelt patterns, soil moisture, and light available for photosynthesis. Incoming solar radiation or insolation originates from the sun, is modified as it travels through the atmosphere, is further modified by topography and surface features, and is intercepted at the Earth's surface as a direct, diffuse, and reflected component. So, in this illustration, you can see the sun cloud dust. From the direct radiation, it is intercepted and impeded in a direct line from the sun. Meaning, it is intercepted and impeded in a direct line from the sun. This is the direct. And diffuse radiation is scattered by atmospheric constituents such as the dust and the clouds. So, the diffuse radiation is scattered by atmospheric constituents such as the clouds and the dust. And this is the diffuse radiation. And lastly, the reflected radiation is the surface features. Surface feature is this. This is the reflected radiation. And to solve the total or the global solar radiation, it is the summation of the direct, the diffuse, and the reflected. This is for the total or the global solar radiation. Generally, direct radiation is the largest component of the total solar radiation, and the second largest of the total radiation is the diffuse radiation, and the reflected radiation is the constituent only small proportion of the total radiation, except for locations surrounded by a highly reflected surface such as a snow cover. And now, there are three ways to calculate the radiation. First is the global radiation, the second is the direct radiation, and the third is the diffuse radiation calculation. First is the global radiation calculation. Global radiation calculation is calculated as the sum of the direct and diffuse radiation of all sun map and sky map sector respectively. The global thought is meaning the global radiation direct thought is the direct radiation and the diff thought is the diffuse radiation. This is the way how to solve the global radiation calculation. And the second way how to calculate the radiation is the direct radiation. There are 4 ways how to solve the direct radiation. First is the total direct insolation for a given location is the sum of the direct insolation from the all sun map sector. Diff dot meaning the direct insolation and the DIR theta E meaning the direct insolation from the sun map sector. Theta means in the direct insolation is the zenith angle, and the letter E meaning is the azimuth angle. The direct insolation from the sun map sector with a from a centroid of a zenith and an azimuth angle is calculated using this second equation. The second equation is calculated using the direct insolation from the sun map sector with a centroid and a zenith angle and the azimuth angle. This is the second equation, where S constant is meaning the solar constant. S constant is the solar constant multiplying by the transmissivity of the atmosphere of the overall wavelength for the shortest path in the direction of the zenith, and multiplying by the time duration represented by the sky sector for most sector is equal to the day interval. For example, a month multiplied by hour interval. For example, a half hour for a partial sector near the horizon. The duration is calculated during the spherical geometry. By the way, to the power of the transmissivity, meaning the relative optical path length, as measured the proportion relative to the zenith path length, that you can see here in the equation number 3. And after multiplying the time duration represented by the sky map sector, you can multiply the sun gap theta A, where sun gap meaning the gap fraction for the sun map sector. We're multiplying this. lastly, the cosine angle of incidence, the centroid of the sky sector, and axis normal to the surface, where this mean the angle of incidence, that is the angle of incidence between the centroid of the sky sector and the axis normal to the surface. And for the third equation of the direct radiation calculation is coming from the power of the transmissivity, where the relative optical path length that measured as a proportion relative to a zenith path length, where the relative optical length, or the m times the theta, is determined by the solar zenith angle and the elevation above sea level. For zenith angles less than 80 degrees, it can be calculated using this equation, where theta is the solar zenith angle and the here is the elevation above sea level in meters. And that's the equation number 3 for the direct radiation calculation. For the last equation of the direct radiation calculation is coming from this angle of incidence between the centroid of the sky sector and the axis of the normal to the surface. From the effect of surface orientation is taken amount by multiplying the cosine of the angle of incidence, between the intersecting surface and the given sky sector with the centroid zenith angle and azimuth angle is calculated by using this last equation, where A times cosine multiplied by cosine theta times the cosine GZ plus the sine theta times sine GZ times cosine this and minus cosine times this minus GA, where GZ meaning the surface zenith angle and the GA meaning the surface azimuth angle. For the zenith angle greater than 80 degree, refraction is important. So this fourth equation is how to calculate the direct radiation. And now, the last calculation for the radiation is the diffuse radiation calculation, where the diffuse radiation at its center is calculated integrated over the time interval and corrected by the gap fraction and angle of incidence using this equation, where RGLB means the global normal radiation multiplied by P diff, or by the diffuse proportion global normal radiation flux that is diffused, typically it is approximately 0.2 for every clear sky condition and 0.7 for every clouds sky conditions. And multiplying by DUR, and DUR means the time interval for analysis. And multiplying by the sky gap theta A, sky gap theta A meaning the gap fraction proportion of visible sky for the sky sector. And multiplying by the weight theta A, where weight theta A meaning it is the proportion of diffuse radiation originating in a given sky sector relative to all sectors. Relative to all sectors, the weight theta A. And multiplying by the cosine times the angle of incidence between the centroid of the sky sector and axis normal to the surface. Times the cosine of angle of incidence between centroid and intercepting. Right. So this is the first equation for the diffuse radiation calculation. And for the second equation for the diffuse radiation calculation is getting from the first equation, which is the total or the global normal radiation can be calculated by summing the direct radiation from every sector, including the obstructed sector without correction for angle of incidence, then correcting from the proportion of the direct radiation, which equals to 1 minus P diff. So this is the second equation. So get this for the first equation. And for the third equation, for the diffuse radiation calculation, it is for the uniform sky diffuse model, where weight theta E is calculated as follows. So we weight theta E, is the proportion of the diffuse radiation originating in a given sky sector relative to all sectors, where cosine theta to the 2 minus the cosine theta to the 1 over the div AZ, where theta 2 and theta 1 meaning the bounding zenith angles of the sky sector, and the div AZ is the number of azimuthal division in the sky map bounding zenith angles of the sky sector, the theta 1 and the theta 2, and the div AZ is the number of the azimuthal division in the sky map. For the last equation of diffuse radiation calculation is for the standard overcast by the sky model, weight is calculated. Where weight is calculated, where weight is the proportion of diffuse radiation, where weight theta E is equals to 2 cosine theta to the 2 plus cosine 2 theta to the 2 minus 2 cosine theta to the 1 minus cosine 2 theta to the 1 all over 4 times the number of azimuthal division in the sky map. So, for the total diffuse solar radiation, for the location where is calculated as the sum of the diffuse solar radiation from all sky map sector, where div dot is equals to the summation of div theta E, where div dot meaning the total diffuse solar radiation, and the div theta A meaning the diffuse solar radiation. So this is the 3 calculation for the solar radiation analysis. Solar radiation analysis. Incoming solar radiation or insolation is a driving force for the Earth's physical and biological systems. Knowledge of the amount of the insolation at a specific geographic location is helpful for application in diverse fields, such as agriculture, resource management, meteorology, civil engineering, and ecological research. For example, knowledge of how much sun an area receives over a period of time may be useful in determining a new site for a ski resort or the best location for growing specialty crops where specific microclimate conditions are needed for optimal growth. In other example, insulation maps have proven important for predicting the behavior of forest fires and making decisions concerning the best firefighting methods. For civil engineering and urban planning, insulations can be important input for suitability models used to determine optimum sites.